good morning, and I see several familiar faces, but lots of faces that I don't recognize. So I think that makes it a good mix for this conference. And I'm going to talk about today, we're going to start actually with your brain. And so we're going to explore your brain just a little bit. And I know that may sound dangerous, especially at 9 o'clock in the morning. It may not be quite up and running yet, but that's what we're going to do here in just a minute. And I have a very specific reason for exploring your brain and how it operates. So let's jump into it. So here's some of the key points I want to make today. First of all, that the brain can be modeled as two systems. How many of you already believe me that your brain has two independent systems? Absolutely 100% believe me. Okay, two basic systems. Okay, I only saw a couple hands go up, so let's see a little bit later this morning if you agree with me. So as we move ahead into the artificial intelligence era, you know, we have two really key tools in memory to make that happen, and that's DRAM and NAND. And I like to say the future of NAND is NAND. The future of DRAM is DRAM. And I stole that from somebody about 10 years ago. And it's still true today. But there are alternatives that are coming, and we're going to talk about how those emerging memories can be used to solve some of these limitations that we have with DRAM and NAND. So if you're at Micron or Toshiba or Samsung or Hynix, don't worry. You know, your technologies aren't going away overnight. And all of us that are designing memory or storage systems around that, we don't have to throw out that knowledge, but we do have to learn about the new technology. So we're going to talk about that. And then the key point here is that emerging memory, as it gets commercialized, helps accelerate this movement into the AI era. So when S.W. Wirth asked me to talk, he said, I asked him over the phone, I said, well, what do you want me to talk about? And he says, anything you want. And I thought, well, that's really dangerous. It could be anything. But this is a book I'm working my way through. And how many of you read this book? Okay, only a couple hands. I really highly recommend it to you. And I'm just going to give you a tiny little taste of why I do that. This is a gentleman who is a professor. He's a professor of psychology, yet he's done this work very scientifically over decades of time. And what it describes is that we do have these two systems in our brain, and they really help us in how we think and make decisions. So a lot of the book, which we're not going to go into here, but is actually how our brain works and biases our decision making. So these two systems, the one is a very fast, intuitive system. Takes no effort. The other is more deliberative, reasoning, etc. All right, you ready for a quiz? I know it's 9 in the morning and you're going, gee, do I have to use a number 2 pencil? I wasn't ready for a quiz. I didn't study last night, but here we go. I'm going to show you two images. Don't say anything, just I'm going to show those two images and then we'll talk about what happened. Okay, what happened in your brain? You saw two images come up. We're going to go into this. And by the way, this is exactly the example that he uses in the book to lead off. You saw this image on the left-hand side. And immediately, what did your brain do? What are some things you thought about? What's her emotion? She's angry. You know, who is this person? You might have said, that's my wife, my sister. Somebody here I met yesterday at the conference that wasn't very happy with me. You know, you came to a bunch of conclusions immediately. You probably even might have assumed, what are her next words? Not very positive, right? You have a model in your brain. As soon as you saw that image, you called up that model. And you had certain assumptions about it. Now, maybe true, maybe not. But you were automatically geared, without any effort, to have certain information, you retrieve that information immediately. How about on the right-hand side? How many of you solved that problem right away? Okay, a handful of you math nerds probably did. It turns out that we can hold like two-digit numbers. If I came back a couple of minutes from now and asked you what problem was I asking you to solve, you'd remember those numbers. But you parked it. You recognized it as an equation, but you said, I can come back later and solve it. So the system on the left is your intuition system. It actually uses associative memory. And there's models built in your associative memory that you had instant recall. The one on the right, you parked it and you gave an interrupt to your reasoning system to say, do I have to solve that now? If I have to solve that now, I know I can go do it, but I'll kind of do that offline. I'll do that in the background. I'll park that and come back. So these are the way our two systems interact. The intuition system is immediate. The reasoning system is interrupt driven and gets called by the intuition system and says, what do I need to do with that information? Now, what are some more attributes about these two systems? So in the case of the intuition system, like I said, it's lightning fast. It happened right away. How many of you did it take effort to recall that model? I bet none of you took effort to immediately have a response there. So it's real time and it's approximate. You didn't know who that woman was, but again, you might have assigned it to somebody you know in your life, etc. Now, how about the reasoning system? Oh, I'm sorry, intuition, if we think about where that happens for compute, that happens on the edge. And this is as we push compute towards the edge, this is one of the things we want to have there. How about the reasoning system? The reasoning system is slow, it's deliberative, it's very precise. In other words, you could give an answer, you could multiply 17 times 24 and give a very precise answer, but it takes effort. And actually, science shows that when we invoke our reasoning system, we burn power. Our blood pressure goes up, our attention goes down. Think about it, when you're concentrating on solving a problem and applying effort to it, you miss things around you. There's actually, they talk about in the book that there's a very famous experiment where they say, watch these basketball players and tell me how many times they pass the ball. And so if you're concentrating on counting the number of times that pass the ball, you miss in the background somebody in a gorilla suit comes by and waves their arms. How can that be? You're focusing on counting. Your reasoning system is taking over and consumes all that power. So this reasoning system is what we have in our data centers, and it's what we have traditionally for compute. Okay, let me see how many of you now believe that you have at least two systems in your brain. Okay, a few more hands, so I convinced some of you. So again, this is just a little bit of taste from that book, but I, again, highly recommend you read it. Now let's go on. We're going to spend most of our time talking about the reasoning system in the data center because that's something you can go build today with the components you have today. But we will come back and talk about the intuition system at the edge. So if you recognize this guy, Dr. von Neumann, he gave us an architecture a long time ago for our reasoning system. It works really well. It works really well. What do we have for the intuition system? Well, there is a guy that's pretty similar, and his name is Dr. Moda. And he's from IBM. And maybe someday we'll talk about Dr. Moda the way we talk about Dr. von Neumann. And Dr. Moda, and this is literally the mapping of a monkey brain. No, they have not dissected human beings to map the network in the brain, live human beings, to map the network in the brain at this point. But one of the things he teaches is the architecture that we've used for reasoning systems is not the architecture to be used for intuition. So someday we may talk about him in the same sentence or the same way, but we're going to store him. So if you're a load and store person, we're going to store him for now. and we'll come back later and talk about him. But let's go into the reasoning system because we want to talk about the memory tools we have today and the ones we have tomorrow. So as we look at that von Neumann architecture, there's that memory unit. And a long, long time ago, we had HDD and we had DRAM. We were pretty happy with that. But then this thing called NAND got invented. And so we replaced it. And for a while, we're happy with this situation. But there's some problems. So let's go in and talk about what are some of those problems in our von Neumann architecture with DRAM and NAND. So my friends at Rambus, this actually comes from Gary Bronner, if you happen to know him. He's presented it a couple times. And what he does show is the ASP, the selling price for DRAM and NAND. There's an old axiom that memory declines cost-wise at 30% per year. And if you map that out, that actually goes back many decades. However, we see a big problem here on DRAM, and DRAM is flattening out. So its rate of change, now ASP and cost are not the same, that is true, but the rate of change in DRAM has really slowed over the last decade. So there are scaling limits, fundamental scaling limits for DRAM, the way we've known DRAM, that are causing its costs and subsequently its price to flatten out. Conversely, NAND is continuing along pretty much that historic curve of 30% per year. So NAND's doing pretty well on pricing, but bottom line is DRAM costs too much. And a friend of mine, Mark Webb, who's another consultant that speaks, he has a great quote on that. He says, well, and 0 of the DRAM manufacturers are concerned about this. They love it. They're making lots of money right now. And if you're a customer, you're not too happy about that. Okay, so let's go on and talk about NAND. This is a look back at 2015. Again, I stole this one from Mark Webb. He had this nice talk at Flash Memory Summit this year. What about latency? Well, what we see is there's a continuum of latency, but there is a big gap between NAND and DRAM. This is where we go from latency of hundreds of microseconds down to tens of nanoseconds. So that is the gap that we'd like to fill. And certainly there are new memory technologies that help us fill that gap. So that's the other problem. NAND is too slow. So let's sum that up. So what are our limitations? DRAM costs too much. NAND, it's latency. The latency is too long, specifically the read latency for storage systems. Okay, so what do we want to do about that? Well, we have this general category called emerging memory. I don't even call it persistent memory or storage class memory. It's just all different types of memory that are coming forward. And from talking to customers, what we hear is that it has to be a cost about 1/3 the DRAM cost or price in order to be interesting. We used to say half, and now it seems to be 1/3. Seems to be the good target. How about latency? Well, the read latency of an emerging memory needs to be below 1 microsecond. And I mean for the system, not just the memory chip itself, not just that simple element, but it has to be all the way through. And as a matter of fact, there's only some workloads that can be handled at 1 microsecond. And those are some of the streaming workloads can be 1 microsecond, but you have to get down to actually 500 nanoseconds in order for it to be used for all workloads. So that's what we're hearing from architects today. Well, in this category of emerging memory, does it even exist? Does something like this even exist? So I used this slide a couple of years ago at a talk I gave at Flash Memory Summit. And these don't even come close to all the switching mechanisms. There's actually an excellent talk and paper. I wish it was on video, but a guy goes through and presents this great memory switching, and it turns out it's a banana. He put 2 electrodes in a banana and showed it switch. So I like to say any fool can get anything to switch, just about. So there's lots and lots of switching mechanisms. Now, he had a talk yesterday, I believe, which was more on the physics itself and the mechanisms of switching. So I'm not going to go into that. But this chart gives you some idea of the diversity of physical effects that are there, and there's probably half a dozen missing from this chart. So the bottom line here is there's too many switching mechanisms. There's almost an abundance of choices. But let's dive in to a couple that have seen some work being done over the last decade. And on the far left is MRAM, specifically spin-torque MRAM. That's the latest type, which gives us the speed we need. The middle would be PCM, it's phase change memory. Years ago, I like to call 3D Crosspoint rebranded phase change. I see Amber in the back has shown up now, so I'll pick on Amber later. So Intel has a lot of names for this. This is Optane technology, 3D Crosspoint. The mechanism is known as phase change memory. And on the far right is resistive RAM. So these are the three that have been researched a lot. There has been some limited commercialization of these technologies, both in the case of standalone as well as embedded memory. So instead of getting into the physics, the science behind it, let's look at companies, let's look at who's doing what in this area. And this tends to change every couple of years, so I had to update this chart. So on the far left, I spent past couple of years working on spin-torque MRAM, and one of the places where there's a really good value proposition for spin-torque MRAM is in the embedded space. So as an embedded memory, we now have announced there are four different foundries, three of which you can design on their PDK right now with spin-torque MRAM at a 28 or 22 nanometer node. So this technology is really coming forward. And that's being used for code storage as well as some caching. Now in the standalone space, there's one company, which is Everspin, which has brought products to market. And so we're going to talk about them a little bit later in that area. Now how about in the middle? In the middle with phase change memory, there's Intel and Micron, who unfortunately are getting divorced after a number of years, but have pursued this technology. And we're going to talk quite a bit about 3D Crosspoint and its relevance to both storage and memory systems. In the embedded space, ST Microelectronic is the lone holdout, but continues to develop this technology for embedded. And then finally in resistive RAM, I used to have a lot more companies up here. It seems like resistive RAM is slowing down a little bit. We're not seeing the same adoption in the industry, et cetera. So there's fewer companies pursuing it. In the embedded space, Panasonic has developed a very nice technology, and Crossbar also has licensed their technology to Foundry, although we haven't seen as much uptake of that technology as we once thought. In the standalone space, Adesto has shown their version of resistive RAM, which is conductive bridging RAM, and that's for relatively low density and almost can be considered embedded. And then at Flash Memory Summit this year, Sony talked about pursuing a resistive RAM technology that is in the hundreds of gigabit range, but is still years out. So let's focus in on things which are shipping, certainly sampling, and products that are shipping, because again, we want to apply this to our data center, to our reasoning system, and we want to see what can we build with these emerging memories that exist today. Now I realize, and even later today there'll be a talk on another technology, there are dreams of many other sorts of technologies. I put a splash of letters up here because it always seems like there's a new one every year that gets talked about. But we don't see evidence of that. There's no samples, there's no products, there's nothing we can build with that. So let's be mindful of these other devices. Although I'm still really curious about Micron's new memory B and when we're going to see that, and what it is. Okay, so let's go back to the key question, does such an emerging memory exist that gives us 1/3 the cost of DRAM and a read latency of less than 1 microsecond in the system? 3D Crosspoint doesn't really cost 1/3 of DRAM, according to my friend Mark Webb. And the latency is not less than 1 microsecond. Oh, that's a problem. How about MRAM? Okay, let's look at MRAM. Okay, MRAM's got the low latency, but if there was a hell no symbol for cost, I would have used that. I mean, it's not even close. It's really, really expensive. Yeah, middle finger. Okay, yeah, you're right. I didn't think of that. Good ad, good ad. I like that. Oh, so that's not good. That's not good. Okay, so our emerging memory candidates, neither of them meet our targets. And this is one of the lessons, guys, is that, you know, we keep setting up these targets. I actually don't like storage class memory as a definition. If you go back to the original IBM paper, they define something which my 30 years experience tells me will never happen. So we have to be a little bit careful about that. And so I want to follow on that comment with, I call it the R word. I don't like to say it, replacements. And those of you old enough to remember The Graduate, that's what it's taken from. But there are no replacements. There are no one-to-one replacements in the memory business. And I could go back in history and prove that to you. The system always changes around the lowest cost memory, the smallest cell size. So stop looking for those replacement technologies. They don't exist. They're not going to exist. So we're moving from a NAND DRAM world to one with combinations of memory. So now let's apply that concept to the technologies I just showed, and also talk about what products are being built with those combinations of technologies. Okay, so on 3D XPoint, what can we do? Well, we can combine that on the memory bus itself with other DIMMs of DRAM, and to give us a winning combination to give us that reduced latency. So that allows us to achieve very low latency from a system point of view. So maybe the raw memory technology itself didn't give us that 500 nanosecond read latency we wanted, but how can we architect around DRAM and combine the two, 3D XPoint plus DRAM, to get there? Didn't do anything for cost, though. So again, I think that's one of the challenge for the manufacturers here, is keep bringing the cost of that technology down. How about an MRAM? Well, in MRAM, we had a cost problem, so let's combine it with NAND. NAND is a lot cheaper than DRAM. How do we combine it? And so by combining MRAM and NAND and working those two together in a system, we can achieve our goals, both low cost and low latency. Okay, so what are some products? Again, Flash Memory Summit was last month, so good time to talk about this. What are some products that we saw at Flash Memory Summit that featured emerging memory and actual things that were being demoed? Let's put it that way. Well, certainly Intel Optane DIMMs are very exciting. And this is putting that technology, 3D XPoint, putting it on the DDR bus. So Intel has done a variant of the DDR4 interface, and you put both of these types of modules there. And this came straight from their talk that they gave at Flash Memory Summit. And what we can see is, even in a module, these are very high capacity. Hundreds of gigabytes going to terabytes on a single DIMM. That's pretty exciting, especially when DRAM scaling is slowing down. And has been pointed out, even on DDR5, we're kind of expecting the highest capacity might be 32 gigabytes of DRAM on a DIMM. So these are really big numbers. So nice job there on the capacity. Now, Intel is focused very heavily on architecting the whole system to make it useful. And I think that's been an excellent effort that we as a memory community owe a debt to Intel in sponsoring that work. Part of that has been done through SNIA in the persistent memory twig. And it's a total effort to look at the architecture, the software, the hardware, everything necessary to take these new memory technologies and make them as useful as possible. So this chart here is showing latency, showing the stack up of the drive itself, the controller, and the software, and how by architecting all the way down to a special variant of the DDR4 bus, what that looks like. And what they're saying is we got the latency really close to zero. Unfortunately, it's not less than 1 microsecond, but it is just a couple microseconds. So, again, good job. And so what happens here is you have the DRAM as near memory, and then you use the Optane, the 3D XPoint as far memory, and that gets the overall system latency where you need to be. And then the bottom line is you can get terabytes of a memory pool that each of your processor clusters can talk to. Now, what's the only downside here? From my point of view, it's that it's Intel controlled. So if you want this technology, you're locked into Intel. If you want a wider supply base, kind of out of luck. So again, that's one of the disadvantages here. But we'll come back and talk about other efforts in that space. Now let's switch to our other technology, which was MRAM. And what did we see from IBM this year? We saw from IBM this flash core module that combines MRAM and NAND. And it uses just a small amount of MRAM for a very fast persistent write cache. And that allows you to do logging, journaling inside. And the nice thing about this, as described by the architect, this is Brent Yardley from IBM that talked about it, is that it goes with the drive itself. So you no longer have to worry about backing up things that you might have outside of the drive. It's all internal. So this is a case where a small amount of MRAM with a large amount of NAND is giving us that low latency and that low cost that we want. So these are two of the technologies here that we talked about and where they fall on that latency spectrum. And they do a pretty good job of filling that in and giving us new options for storage and memory systems. There are a few other things, though, that are in there, and I'm not going to spend too much time in this talk discussing that. But let's talk about what are some of those other memory combinations or other things you might want to know about as we try and fill in this latency spectrum and give more options to storage system architects. So other stuff that I saw at Flash Memory Summit this year that you might find interesting. Apologize for the poor graphic. It looks like a spy graphic, etc. I think it largely was. Toshiba didn't post their presentation this year, but they announced something called XL NAND. And I like the graphic a lot because typically NAND is architected just to give you the highest density per square millimeter of bit cells. But what they're doing now is they're architecting inside the memory chip itself as all these small tiles. And when you have small tiles like that, you can do a massively parallel access, reduces the latency. So that was the nice part about it. And they're saying it's a 10-time reduced latency versus TLC. So again, this is not a new technology, but this is a new design architecture utilizing NAND to deliver lower latency. So that's also a trend. It's still not 1 microsecond. Sorry about that. But it does give us something that's new. How would you use this? And I think the way you would use it seems to be a market that it's starting to get going, which is very low latency SSDs attached to compute nodes that are not part of the storage system. Maybe they're attached to the networking system itself, somewhere like that. So there seems to be this development of new capabilities or new products that are trying to attack that market for low latency SSD. There are some competitors here. Intel has their Optane SSD, which is 3D XPoint itself, which is out there in the market. And there's also Samsung ZNAND, which is doing something similar, which is let's just make NAND faster. So that's one of the things that I saw that also helps fill in that latency spectrum that we talked about. What's an activity that goes outside of that Intel-controlled environment is in JEDEC. There's work being done on something called NVDIMM-P. And I know there's multiple versions of NVDIMM. We seem to like funky nomenclature in this industry. Too many letters and hard to keep track. You need a decoder ring. But the idea here is that this now, you re-architect the DDR5 bus to have a protocol which handles non-deterministic behavior. So non-volatile memory needs non-deterministic behavior. When you give a write command to an NVM, it doesn't know necessarily how long it's going to take to write. So it needs to have that ability to stall the host, etc. So this is an effort to do that without interrupting the progress of the DRAM on the same bus. So we're headed towards a future here where the memory bus is used for two different types of memory, volatile and non-volatile, with different characteristics. So we need a different protocol. And Bill Gervasi, who's going to be speaking later today about Nantero's technology, he talks about it being a non-determinist credit-based system. he says time for cleanup, but basically it's holding off the host and having this ability to do both. So this is a very interesting activity, and it is intended to be an open standard. It'll compete with the Intel Optane DIMMs, but it's backed by all the major memory companies. Now if we could just get a major processor company, AMD, I'm looking at you, to sign up, then things would be good. So I think that's what's needed here, is still support from the processor companies. So this is something to keep track of. So let's sum up. This is kind of what I put together for you, your cheat sheet, your watch list, things I learned from Flash Memory Summit this year, things to keep watching. I think the Everspin MRAM in low latency SSDs is an interesting one. We'll see how IBM does with their FlashCore module, which is the first implementation of this. I think Intel's 3D XPoint in the Optane DIMMs for server memory continue to be a very interesting space. It's easy to make fun of Intel and say you overpromised and underdelivered, but at the same time, we do expect that hundreds of millions of dollars of 3D XPoint will be shipped within the next few years. So it is still the largest leading emerging memory effort that's out there. So, so I'll rein in my making too much fun of Intel. The Toshiba XL NAND, I think we're going to see more of this, how to make NAND faster and give us lower latency. And then finally that NVDIMM-P. So that's your watch list. Now let's go back and let's load Dr. Moda and talk about intuition at the edge. So I'm going to switch gears. So this is a really different topic. It's one I personally find extremely interesting. Now, what are some things that Dr. Moda has taught us? And this came out of a project IBM called True North. I think they have a new name for it now. I don't happen to know what that is. Your intuition system in your brain operates on 18 watts of power. You do a lot on 18 watts. Give yourself an A+. All right, way to go, brain. You are super efficient. If we took a von Neumann architecture, took it to the edge to do everything your intuition system does, that takes more than 20 gigawatts. In other words, it ain't working. You cannot use a von Neumann architecture. It will not be energy efficient enough to do your intuition job at the edge. Also, if we look at the architecture of the monkey brain, what we see is a lot of little compute nodes with a lot of networking. And it's quite fascinating, actually, to follow through that, the different elements of your brain and how it's networked. So we have a highly, highly networked, again, it's what IBM, I think, used to call in the past mesh computing. And so it's an old idea brought back again. How can we implement that? Now, one of the things that there's very good evidence for, including excellent academic papers and some industry papers now, are showing that trained neural nets perform that lightning fast intuition. Now that makes a lot of sense, because when I showed you the picture of the woman at the very top, you called up immediately a model from your associative memory. In other words, you store all these models. You know, if I said the word room to you, you'd immediately call up a model. What does it look like, et cetera. So you have all these models. Makes sense that we would have these trained models stored somewhere in our brain. And neural nets do that extremely well. Now, an interesting way that you can use emerging memory is to hold the weight inside a trained neural net. So again, that's the way we're storing information, and it's a very compact way of storing. And when I say hold a weight or an analog memory, this is like MLC plus. This is lots and lots of levels. And I'll show you a little bit how we utilize this. Once we have the weights, then we want to access this array in parallel and then sum the weights to choose which model is the best to apply to the situation. So that's using what I call analog combined circuitry to run that through and then find that correct model. And keep in mind, this is an approximate, right? Our intuition system gives us an approximate answer. It doesn't need to be precise. So the most efficient implementation is using analog memory, and that might be 6 or more levels per cell. I mean, again, IBM did some work on this that showed 5 to 6 levels is particularly good for this. Here's a nice thing. You don't need 7 or 5 nanometer processing. And one of the most amazing things that I've seen is we see 28 nanometer chips utilizing this technology outperforming 14 or 16 nanometer FinFET by a lot. Now that's power efficiency, that's prediction accuracy, it's the architecture. The architecture is much better than using a GPU and doing lots of matrix math. So as the architecture changes, the cost paradigm changes. Now this makes sense to do at the edge. And some of those places we'll talk about in a minute are in vision or image processing. How many of you have heard of this company called Mythic IC? Okay, very few. And maybe a few years from now you'll think back and say, yeah, I heard about that. They're a startup. I don't know if they'll succeed. But they're doing something very interesting, and I also like that they have competitors. There's one called Sentient in Southern California. They did a paper at Hot Chips that was a fascinating paper. Some of their members don't like it, but their CTO went and posted all the slides online and did a full explanation. So if you're interested in this topic, search Mythic at Hot Chips 2018. And you can find a very, very good description of their technology and how they implement it, as well as a good walkthrough of neural nets and why you should care. I'm going to touch on a couple things really quickly. Over on the right-hand side, this is the memory array itself, just shown as a 3x3. So each individual memory cell that's acting as an analog device, you think of it as a variable resistor. And then what we're doing down here is we're actually we're figuring out how much current when we access all these things in parallel. So that is what helps us decide what model to choose. Now it's a blended system because while this is the neural net in the middle in this single tile, you can see that there's some digital logic using von Neumann concepts that are driving it. So it's not just a non-von Neumann machine, it's a mixture, a blend of the two. Then one of the things we mentioned very quickly when we talked about the brain is that there's several compute nodes, and then you put them together in this mesh or sea of tiles. So again, this architecture is very close to how our brain operates, and gives us results similar to how our brain operates. And they plan on using it for vision and image recognition and voice recognition right now. They're currently using embedded NOR flash because it exists. It's easy to integrate, and it holds those weights in that analog mode. Okay, another company, that's my takeaway for it, what you get out of that. Another company that presented at Flash Memory Summit was Crossbar, and what's interesting is Crossbar has kind of gone in this direction of AI and the application for resistive RAM in that space. And they also talked about, here's their specific describing the flow of how information goes through and how an RRAM array in a trained neural net can do that. So that's, I think, an interesting question, is RRAM a technology which is especially suited for analog memory and neural nets? Okay, so those are two examples of companies that are doing interesting things in this space. So one of my favorite questions to ask, whether it's somebody else speaking or when I'm preparing to speak, is why do I care? And hopefully not too many of you are thinking that right now. Hopefully I've made my case of why you care. But let's recap a little bit. What is emerging memory enabling in artificial intelligence? And I think in the data center it comes down to this. How do I get terabytes of memory, a larger memory pool that I can access? More data, better decisions. Better training, better decisions, more precise outcomes. So how do we get that larger amount of memory to operate on? On the edge, we talked about having this analog memory in this new architecture and then giving us this brand new capability, which our brain does, but our compute systems don't do very well, which is that lightning fast intuition at very low power. So again, I think this is the major takeaway of how I am stating that emerging memory accelerates us for AI. Okay, final wrap up, takeaway points. Your brain has two distinct systems, and I saw more hands go up, so let's see it again. How many now believe this? Yeah, I think there's a lot more hands. Okay. And so good, I think I've made that point there. Our reasoning systems that are based on DRAM and NAND need reduced latency and cost. And I gave you very specific numbers about what we want to achieve. Unfortunately, none of our memory candidates do a one-to-one replacement. And so stop thinking about memory as a one-to-one replacement, but think about combinations. How do we combine different memory technologies to achieve the system-level goal? And then in the last section, I wrapped up with the intuition systems really do require that new architecture to get us to operate at low power. And we utilize emerging memory as analog, in an analog mode to hold those weights. And the goal here is to accelerate both the performance and the adoption of AI systems. Okay, advertisements. I get to wrap up finally with advertisements. So Persistent Memory Summit is coming. This is a very popular event. If you haven't signed up before, you can literally register right now. You can take out your laptop and bring it up and register right now. And I advise you to do it because it's standing room only. And I think the progression of the industry can be clearly seen through every year the advance in persistent memory adoption at that. And then finally, this is my advertisement. And if you want to follow me, you can track me on LinkedIn or on Twitter. Okay. Very good. Thank you very much. Do I get to introduce Amber? That could be dangerous.
We have time for questions. We have 10 minutes.
Good. Thank you.
I don't know where that is coming from. Lucy has it.
Lucy. All right. Raise your hand. You got a question?
Dave, you might want to mention why persistent memory zone is being held here instead of downtown San Jose this year.
I don't know the answer to that, Jim. Jim, would you please give us the answer of why it's being held here? It's huge. It's huge.
Jim Pappas finally gave in. Other questions? If not, all right. Thanks, Dave.
Oh, Tom's raising his
Tom.
hand.
I'll give you one.
He doesn't need a mic.
Probably not. Can you hear me? So, Dave, one thing you didn't mention on some of the neural network processing is sort of indirectly got into it with the in-memory processing, and in particular, I know because of your background, maybe you can speak a little bit about those two items.
Yeah, I think there's two different spaces, and so yeah, I'll repeat the question or I'll rephrase the question from Tom. He was talking about to widen out a little bit and talk about the application of emerging memory to more of the tasks. I focused on the intuition system at the edge. There certainly is, and I think NVIDIA does a very good job of explaining it. So if you want to reference material of why we do training in the data center, we do training right now today with GPUs and lots of SRAM, and sometimes we use DRAM. So that's the training function done in the data center. Edge we talked about. In the data center for training, SRAM scaling also has had difficulty and is getting more and more expensive. So there is a need to bring more memory into that space, and in particular to have it be persistent. This is, in particular, is a task where that standalone STMRAM can go and offer new capabilities in that training function. That can be very helpful as you're doing the MAC operations and doing that matrix operation, to have that be non-volatile and be able to store entries at relatively low power and go back and forth. So I think that would be my quick way of answering that. That there's application for other emerging memories to other parts of the AI system in the data center for training.
I'm trying to think ahead of this. Are there any implications as you do this design for less network traffic, say over cellular networks, because you're able to do more processing?
Sure.
Yeah. This is my daughter, by the way. Thanks, Lucy. So that you're able, because you're able to do more processing at the edge, you're not shipping back and forth all the data to the server farms, and perhaps more latency in my great phone here, and less latency in the phone, and less data getting stored where it could be mined by people that I don't want it to be mined by.
No question. There are not two levels in an IoT to data center system. I've seen talks by Oracle before that there's 5 different levels. You store and process information of different complexity at each level. In other words, if I want to do something locally and make a decision, I don't want to go back to a data center, AWS data center, hundreds to thousands of miles away. I want to do it right there. There is a time and cost penalty every time you transmit data a long distance. Sometimes referred to as fog computing, intelligence at the edge. How do we do more decision making locally and store less and less, or store more complex information all the way back at the data center? So I think that drives the embedded adoption of MRAM in particular, giving us a high density option of an emerging memory, and allows the integration directly into the SoC. You can see it in your own phone though too, is that the amount of storage capability you have in your own phone is kind of plateaued over the last couple of years. Now we're talking about how do we enable sensors to have enough memory, enough intelligence to do the job so that we can even unburden the mobile processor. So I think it's that multiple layers that we have to think about.
So Dave, we've been watching persistent memory emerge for a long time. In your crystal ball, what do you see in 5 years for?
Sure. What's taking
we call it
so
something
long?
other than emerging.
When the hell are you going to get there? Yes, this is a common question. Usually I'm the moderator and I get to shout that at the panelists. What's taking so long? It's a very good question. I think, again, the leading effort is the total effort that Intel has done. I would continue to look for when do Intel processors ship with the right memory controller integrated that allow access to persistent memory. That's still somewhat limited. Myself, I'm looking at 2021 and beyond, which is a little more conservative than some other estimates. But I think it is taking a while. The NVDIMM portion is still very niche-y. It's still quite small. I hear those producers complaining that they're not shipping enough of it. So again, I think it's going to take still years of time. I don't think this is a hockey stick in 2019. Okay.
All right,
I
thanks,
think
Dave.
we've run out of questions.